Week 2, lesson 7. All right, we're going to start right here. It's asking me to graph 2x plus 3y equals 6. I have a couple options here. I could change that into slope-intercept form, but I think the easier option is probably just to figure out what the intercepts are. If I let x be 0, y would have to be 2. Or conversely, if I let y be 0, x would have to be 3. So it's not too difficult to graph those two dots. One of them is here and the other is here, and then just connect them with a straight line. And there's my line. Okay, so the question here is, what is the slope of that line you just graphed? And again, it's not hard for you to count and go, well, I'm going up 2 and left 3. This slope is negative 2/3. And if then I ask you what is the slope of the line that's perpendicular, you, again, wouldn't have a problem flipping that fraction over and changing its sign. So the slope of the line perpendicular is 3/2. All right, so down here, this says that in 2 dimensions, the coefficient vector is normal to the vector. Okay, so what we just did was all in 2 dimensions. All right, let me show you what this means. The coefficient vector has to do with this. The coefficients there are 2, 3. All right, now just a reminder, this is the change in the x direction, and this is the change in the y direction, which is what we just said when we talked about slope. We just said that that was the perpendicular slope. So if you're looking at the coefficients, you know the slope of the perpendicular. Okay, now here, and again, this is kind of tiny, it's sort of hidden in here, but it follows in 3 dimensions. So take a look at the first example. It says, what is the normal vector to this particular plane? Well, I have no idea what that plane looks like, but I do know the normal vector. It is just 3, 4, -5. It's literally just the coefficients. This vector is perpendicular to this plane. All right, so now that I know how to find the normal quite easily, let's see if we can do this example. So a plane passes through these points. Okay, so these are singular order triples, right? They're not vectors. We're going to find the Cartesian equation of the plane by using a normal. All right, so in order to do that, I need a couple of vectors. So I'm going to figure out vector AB by doing head minus tail, and AC, again, head minus tail. So AB would be 1, -2, -2, and AC is 2, -3, -1. All right, and it says to use a normal vector, so I'm going to find the normal by doing the cross product, I, J, K, with the 2 vectors that I just figured out. So I minus J plus K. All right, again, expansion by minors, you should get 2 minus 6, -1 plus 4, and -3 plus 4, which makes my numbers, when I actually simplify this, -4i minus 3j plus k, which means I have the coefficients, right? I know the normal vector. It is -4, -3, 1 because of this. Okay, so now I'm not done. Right? This problem is asking for the Cartesian equation of the plane. So this is how I'm going to do this. I'm going to start with a point on the plane. Okay? Oh, sorry. Point on the plane. X, Y, Z is, again, I have 3 different points. I think I'm just going to use point A, 1, 2, 1. And if I multiply both sides of this, right, if I do the dot product of both sides of this with this normal, I should get the Cartesian form. Check this out. -4, -3, and 1. Okay, so keep in mind, dot product over here is -4x minus 3y plus z. Dot product on the other side is -4 minus 6 plus 1, or in other words, If I simplify that, I get negative 9. And again, Cartesian form, I would prefer this to be positive. 4x plus 3y minus z equals 9. Okay, now I highly suggest that you try this again with points B and points C, right? Right here, I used point A, right? I just made a random guess. I encourage you to try B and C. Convince yourself that you do get the exact same number.